Hello, my name is Alan Winfield and I am Professor of Robot Ethics in the Bristol Robotics Laboratory here in the UK. Thank you for inviting me to address the Robot Business Fair. I'm very sorry that I cannot be with you in the wonderful city of Seoul in person. In this talk of 5 parts, I will introduce and outline my work in robot and AI ethics. First, I will introduce the subject. Let me share my definition of a robot. A robot is simply an embodied artificial intelligence. An intelligent robot senses its environment, then purposefully acts on or in the world. It is the embodied AI that enables a robot to make intelligent decisions, to act purposefully. This definition usefully links robotics and AI. Ethics are simply moral principles that we consciously or subconsciously use to govern our behaviour. Similarly, groups of people, professional bodies, charities or companies, may choose to follow agreed ethical principles, and society holds some ethical principles to be so important that to choose not to follow them will break the law. As a practical example, a principle might be to treat everyone with respect. Philosophers have considered ethics over many centuries, and there are various well-known principles, perhaps one of the most famous being the Golden Rule: treat others how you wish to be treated. I define robot and AI ethics as concerned with the ethical impact of robots and AIs on individuals, society and the environment, and how any negative impacts can be mitigated. Robot ethics and AI ethics share exactly the same concerns. Here is a word cloud on AI ethics, reflecting that we must work towards robots and AIs that respect human rights, diversity, dignity and privacy, is unbiased and sustainable, transparent, accountable and socially responsible. In practical terms, robot and AI ethics is concerned with how human designers, manufacturers, operators and maintainers should behave in order to identify and address any negative ethical impacts of their systems. So, what do robo-ethicists actually do? Well, we develop ethical principles in order to support and guide the way in which robots and AIs are designed and deployed in society. We develop methods for ethically designing, operating and maintaining robots. We call this values-driven design. We draft new ethical standards in robotics and AI. And we advocate for the adoption of these principles, methods and standards, and, if necessary, new regulation. Next, I ask the question, why are robot and AI ethics so important today? Of course, accidents happen, and that is just as true for robots and AIs as any other technology. Autonomous vehicle fatalities make the headlines. There have been more than 40 that we know about since 2016. And we have almost no data on accidents in human-robot interaction, that is, robots designed to interact directly with humans. Here is one, a security robot, that happened to be reported. A responsible roboticist must be interested in all accidents, whether serious or not. We should also be very interested in near misses. These are taken very seriously in aviation, and there is good evidence that investigating near misses improves safety. Robot pets such as the Paro robot baby seal shown here have shown great promise in providing comfort to elderly people, and especially to those who've had to leave their real pets behind when moving into an elder care home. They have also been shown to have therapeutic value to elderly people with dementia. Although this is undoubtedly a very positive application for robotics, we need to be cautious that users might become over-dependent or emotionally attached to the robots. Some robot pets are also connected devices, and while this might be of benefit if, for instance, the elderly person becomes distressed, we do need to be mindful of the need to respect privacy and autonomy. We should also note that the extent to which an emotional attachment between humans and robots is regarded as acceptable varies widely among cultures. Robot toys are increasingly sophisticated. While many are undoubtedly both great fun and educational, a number of toy robots are connected devices, such as the Anki Cosmo robot. Some are voice-activated, such as the Texter robot puppy shown here. We need to be mindful that any connected toys such as these might be collecting data, including voice recordings, and therefore raising concerns over privacy. In addition, some robot toys employ face recognition AI to learn the faces of the children playing with it. Again, we should be cautious about face recognition, not only over privacy, but also because such technology has been known to learn and recognize all but one child in a group, causing that one child some distress. We can already build remarkably lifelike android robots. Here are two examples: the Actroid robot from the University of Osaka and Kokoro-built Geminoid DK robot double commissioned by Danish professor Henrik Schaefer. These android robots are so lifelike that if you glanced at one across a crowded room, you would assume it is a person. Only if you approached the robot and attempted to interact with it would you realize that it is not a person but a robot. The problem is that we are many years away from being able to design and build a robot's AI so that the robot demonstrates fully human-like intelligence and behavior. Until then, robots like the ones here demonstrate what I call the brain-body mismatch problem. The robot's appearance leads to a false expectation that it will have human-like intelligence. This may not be a problem for you and I, but a young child or someone with reduced cognitive capacity, elderly or disabled perhaps, might well be deceived by such robots. Industrial robots have been displacing jobs for decades. Assembly line robots were first introduced into car assembly plants in the 1960s. More recently, robots have seen widespread use in warehouses. The Hevo Systems robots shown here have been widely deployed in Amazon warehouses. The introduction of these robots inevitably displaced very large numbers of jobs on assembly lines and in warehouses, but historically the introduction of automation has resulted in an overall increase in employment. Job displacement through automation needs to be offset by redeployment and/or retraining. Ideally, the additional wealth created through automation should be used to reskill displaced workers, either directly by the companies themselves or indirectly via taxation. With the rapid development of autonomous vehicles, undoubtedly the jobs at greatest risk are professional drivers. Driverless trucks are currently in development and undergoing real-world trials. In the near term, truck drivers are unlikely to lose their jobs. Instead, I believe they will become vehicle pilots, manually driving their trucks from the depot and onto the highway, then engaging the truck's autopilot. When close to its destination, the driver takes back control to manually drive the truck off the highway to the destination depot. Truck drivers thus become more like airline pilots, but without the salaries and prestige. In the longer term, both truck and taxi driving jobs are likely to be at risk, although autonomous vehicle technology is far from being able to safely and reliably navigate busy city centres. In healthcare, hospital portering robots such as the Ethon tug robot, shown here, have already been deployed in hospitals. However, these robots are primarily used to fetch medicines from the hospital pharmacy to the wards, or to take bedding to and from the laundry. Human porters are still needed to move patients. Although assisted living robots are still an immature technology, some people are concerned that they might be deployed instead of human healthcare workers. Most roboticists think this is both unlikely and undesirable. Instead, assisted living robots should be used alongside human carers. The robot would take care of routine or manual tasks, thus freeing up the human care worker to spend in conversation and human interaction with patients. Robots cannot replace human-human contact. Fortunately, there is an excellent crowdsourced database which collects reports of accidents and near misses involving robots, including autonomous vehicles and AIs. The AI Incidents database covers a very wide range of accidents and near misses. It is well worth checking out. So far, I have not mentioned the energy and environmental costs of artificial intelligence. Given the context of the climate emergency that we are facing, making our robots and AI sustainable must become a priority. But a big problem with AI is a lack of transparency of the true energy and environmental costs. One of the very few papers that estimates the carbon cost of training large AI models for natural language processing, such as language translation, was published in 2019. The carbon cost of simple models is quite modest, but with tuning and experimentation, the carbon cost leaps to 7 times the carbon footprint of an average human in 1 year. And the energy cost of optimizing the biggest model is a staggering 5 times the carbon cost of a car over its whole lifetime, including manufacturing it in the first place. The dollar cost of that amount of energy is estimated at between $1 and $3 million US, something that only companies with very deep pockets can afford. These energy costs seem completely at odds with the urgent need to halve carbon dioxide emissions by 2025. At the very least, AI companies need to be honest about the huge energy costs of machine learning. But of course, AI also involves a huge amount of human labour, and not just the highly paid computer scientists who design and build the AI systems. Less well known is the human labour of mining and processing the raw materials needed to build the giant server farms, as well as the consumer electronics. Then the humans who annotate the raw data used to train the AI models, and finally the humans who dismantle and dispose of the electronics when it reaches the end of its useful life. This labour is very poorly paid and either physically or psychologically dangerous. All of this is beautifully illustrated by Kate Crawford and Vlad Anjola's remarkable Anatomy of an AI System, which shows the Amazon Echo as an anatomical map of human labour, data and planetary resources. The map is far too detailed to see on this slide, but let me just zoom in on the top of this very large iceberg, where we find the Amazon Echo and its human user. I strongly recommend you check this out. It is truly eye-opening. To conclude this section, we can define 4 categories of ethical harm: physical harm to persons or property, psychological harms including deception, overdependency and overtrusting, and there are many more, societal harms including loss of privacy and loss of jobs, and equally important, environmental harms including high energy costs, unrepairable or unrecyclable technology. As responsible developers, we should be working to minimise or mitigate all of these harms. Next, I will explain the link between ethics, standards and regulation. This diagram shows the connection between ethics, standards and regulation. Standards formalize ethical principles into a structure which could be used either to evaluate the level of compliance or to provide ethical guidelines for designers. Ethics therefore underpin standards, but standards also sometimes need teeth, i.e. regulation, which requires that systems must be certified as compliant with standards. Thus ethics, or ethical principles, are linked to standards, which are in turn linked to regulation as shown here. In the final section of this talk, I will discuss emerging regulation for autonomous vehicles, assisted living robots, and AIs. Let us look at one example of a framework of ethical principles in AI. The High-Level Expert Group on Artificial Intelligence is an independent expert group set up by the European Commission in 2018 as part of its AI strategy. Published in April 2019, the framework consists of a set of 7 key requirements that AI systems should meet in order to be trustworthy. The requirements call for human agency and oversight, technical robustness and safety, privacy and data governance, transparency, diversity, non-discrimination and fairness, societal and environmental well-being, and accountability. This diagram shows the interrelationship of the 7 high-level expert group guidelines for trustworthy AI. All 7 are of equal importance, support each other, and should be implemented and evaluated throughout the AI system's life cycle. This process of continuous evaluation is shown at the centre of the diagram. The AI high-level expert group guidelines stress the important and often overlooked need to consider the impact of AI systems continuously and through the whole of the system's life cycle, from conception through design and deployment to end-of-life decommissioning. This chart shows the number of ethical frameworks by year of publication, categorized also by the type of group proposing each framework. First note the very dramatic increase in the number of ethical frameworks published since 2017. Looking at the groups proposing frameworks, we see that 2017 was dominated by professional bodies, including notably the IEEE, the Association of Computing Machinery, and the Japanese Society for Artificial Intelligence. Following Intel in 2017, 2018 saw major technology companies publish ethical frameworks, including IBM, Microsoft, and Google. And perhaps most significantly, 2019 saw ethical frameworks issued by both national government agencies, notably including the Australian government, and by intergovernmental organisations, including the European Council, the European Commission, and the Organisation for Economic Cooperation and Development. In 2019, a very comprehensive survey and analysis of 84 ethical frameworks was published, which lists the principles which appear most often in ethical frameworks for AI. Transparency is the principle most frequently included, appearing in 73 out of the 84 frameworks. The authors of the study note that no single ethical principle appeared to be common to the entire corpus, although there is an emerging convergence around transparency, justice and fairness, non-maleficence, responsibility and privacy. These 5 principles are referenced in more than half of the frameworks surveyed. Standards are a vital part of the infrastructure of the modern world, invisible but no less important than roads, airports and telephone networks. It is hard to think of any aspect of modern life untouched by standards. The International Organization for Standardization, ISO, just one of several standards bodies, lists over 22,000 published standards. Take the simple act of brushing your teeth in the morning. There are standards for your toothbrush, both manual and automatic, your toothpaste and its packaging, and the quality of your tap water. Standards represent a truly remarkable body of work, drafted by countless expert volunteers with an extraordinary impact on individual and societal health and safety. For more detail, please check my short article in Nature Electronics, published in 2019. Almost certainly the world's first explicit ethical standard in robotics is British standard BS 8611, Guide to the Ethical Design and Application of Robots and Robotic Systems, published in April 2016. BS 8611 sets out guidance on how designers can undertake an ethical risk assessment of their robot or system and mitigate any ethical risks identified. Ethical risk assessment is a very powerful extension of the well-established practice of risk assessment to cover the much broader range of ethical risks. As a worked example of the application of BS 8611, let us consider a fictional robot toy called Robot’ın. A paper we published in 2020 considers the ethical risks of Robot’ın within the 4 categories of physical risks, psychological risks, privacy and security risks, and environmental risks. As an illustration, here are the psychological hazards and risks from our paper. These are summarised in a table, together with an assessment of the level of the risk, high, medium or low. First, addiction. Robot’ın might be so compelling that it leads to a child playing obsessively with the robot and neglecting his or her family. A mitigation strategy might be to add a Robot’ın needs to sleep now function as a way of limiting length of playtimes. Second is deception. There is a risk that the child comes to believe that Robot’ın has feelings for him or her. To mitigate this risk, we could design the robot to avoid language that suggests feelings, so that robot never says things like, "I love you." Third is over-trusting by parents. The risk here is that parents become over-reliant on Robot’ın's childminder function. The risk and its consequences are so great as to suggest the childminder function should be removed altogether. Fourth is the uncanny valley. This refers to a fearful reaction when a robot is close to but not 100% lifelike. The risk of this is probably low with Robot’ın, both because Robot’ın is not human-like at all and children are already familiar with teddy bears. However, the risk should be explored by engaging children in early trials of Robot’ın, and if the uncanny valley reaction is demonstrated, it might be mitigated by, for instance, equipping the robot with a cartoon voice. Early in 2016, the IEEE Standards Association launched its global initiative on ethics of autonomous and intelligent systems, with a very clear mission: to ensure every stakeholder involved in the design and development of autonomous and intelligent systems is educated, trained and empowered to prioritise ethical considerations so that these technologies are advanced for the benefit of humanity. The first output from the initiative is ethically aligned design. EAD was drafted by more than 1,000 volunteers across 6 continents, all thought leaders from academia, industry, civil society, policy and government in relevant disciplines spanning science, engineering and the humanities. Ethically aligned design is both a manifesto and roadmap for a values-driven approach to the design of autonomous and intelligent systems. It is free to download and I strongly recommend you check it out. The second output from the IEEE initiative flows from ethically aligned design. It is a series of new standards which address a range of specific human issues at the intersection of technology and ethics. Of the 15 standards working groups launched to date, 6 have led to published standards, highlighted here. I had the honour of leading Working Group P7001 that drafted a new standard on transparency, which I shall briefly introduce now. Following a 5-year process of drafting, review and revision, IEEE Standard 7001-2021 was approved in December 2021 and published in March 2022. It is the world's first technical standard on transparency and sets out measurable, testable requirements for transparency. Using 7001, the transparency of autonomous systems can, for the first time, be objectively assessed and levels of compliance determined. The IEEE Standards Association have made 7001, alongside other related standards, free to download, and I recommend you check it out using the IEEE Explore link here. Transparency and explainability are so important because, firstly, robots and AIs can and do go wrong. When they do, it is very important that we can find out why. Without transparency, finding out what went wrong and why is extremely difficult. And secondly, robots and AIs are socio-technical systems. They are designed to work with or alongside humans who need to be able to understand what they are doing and why. Without this understanding, those systems will not be relied upon. But transparency is not one thing. Imagine you have an elderly mother who is supported at home by an assisted living robot. Clearly your mother does not require the same level of understanding of her care robot as the engineer who repairs it when it goes wrong. In 7001 we define 5 distinct groups of stakeholders. Robots and AIs must be transparent to each group in different ways and for different reasons. These stakeholders split into 2 broad groups: an expert group of safety certification engineers or agencies, accident investigators, and lawyers or expert witnesses, and a non-expert group of end users of autonomous systems and wider society. 7001 defines a different set of normative requirements for transparency and explainability for each of these different stakeholder groups. 7001 also sets out 2 processes for using the standard in practice. System transparency assessment is a method for evaluating the transparency of an existing system, and system transparency specification is a method for specifying the transparency requirements of a system prior to its development. In July 2021, I and other members of the working group published a paper setting out the thinking behind 7001 alongside case studies illustrating both system transparency assessment and specification. In this section, I introduce the work of Project RoboTips, led from the University of Oxford, on robot accident investigation. Imagine that your elderly mother or grandmother has an assisted living robot to help her live at home independently. The robot is capable of fetching her drinks, reminding her to take her medicine, and for keeping in touch with family. Then one afternoon you get a call from a neighbour who's called round and sees her collapsed on the floor. When the paramedics arrive, they find the robot wandering around apparently aimlessly. One of its functions is to call for help if your grandmother stops moving, but it seems that the robot failed to do this. Fortunately, your grandmother recovers, but the doctors find bruising on her legs, consistent with the robot running into them. Not surprisingly, you want to know what happened. Did the robot cause the accident? Or maybe it didn't, but made matters worse, and why did it fail to raise the alarm? Although this is a fictional scenario, it could happen today. This scenario raises the important question of how accidents like this would be investigated and by whom. Do we leave it to the robot manufacturers or instead set up agencies to investigate robot and AI accidents? Accident investigation has a long history. In aviation, the world's first National Air Accident Investigation Agency was established over a century ago, in 1915, and the international conventions governing air accident investigation were agreed in the middle of the last century. The fundamental purpose of any accident investigation is learning. Accident investigations are organised around three key questions. What actually happened? Why did those things happen? And what does that reveal about weaknesses in the design and operation of the system? And how can the system be improved to prevent similar events happening in future? The overall aim of any accident investigation is to come up with practical, achievable and targeted recommendations for making safety improvements. In a paper published in 2017, we argued the case for an ethical black box. Our proposition is very simple, that all robots and AIs should be equipped with a standard device or module which continuously records a time-stamped log of the internal state of the system, key decisions, motor outputs and sampled input or sensor data. The EBB is the robot equivalent of an aircraft flight data recorder. We call it an ethical black box because it would be unethical not to have one. Without such a device, finding out what the robot or AI was doing and why in the moments leading up to an accident is more or less impossible. But accident investigation is a human process which makes use of witness testimony, forensic evidence, CCTV footage if available, and data logs from the accident. In the RoboTips project, we are simulating robot accidents and their investigation in order to both test the EBB and develop processes of robot accident investigation. We believe we are the first in the world to study robot accident investigation in depth. Each of our simulated robot accidents is acted by human volunteers who role-play the subject of the accident, witnesses to the accident, and members of the accident investigation team. All, of course, within the framework of university research ethics approval. We have already staged 2 simulated accidents. The first involved an assisted living robot with the same scenario that I already asked you to imagine. Our second simulation was a smart robot toy that, over a period of several months, causes psychological harm. Within the next few weeks, we will simulate an accident involving an industrial exoskeleton. I will conclude this talk by reviewing standards and regulation for autonomous vehicles, assisted living robots, and AIs, and finish with how we must bridge the gap between ethical principles and practice. In the domain of autonomous vehicles, key recent standards include UL 4600, Standard for Safety for the Evaluation of Autonomous Products, published in 2020, and ISO 39003, Road Traffic Safety, Guidance on Ethical Considerations Relating to Safety for Autonomous Vehicles, published this year. At present, autonomous vehicles, or AVs, do not have a dedicated regulatory body, but are regulated by existing transport agencies. For instance, in the USA, the National Highway Traffic Safety Agency, and in the UK, Highways England, monitored by the Office of Road and Rail. Nor is there yet any explicit regulation governing the operation and use of AVs. By explicit regulation, I mean regulation specifying how autonomous functions are certified as safe. Note that the reason it is legal to drive a vehicle with driver assist functionality is that the human driver is required to be alert and ready at any time to take manual control of the vehicle to recover from a dangerous situation. Serious AV accidents in the USA are investigated by the National Transport Safety Board, NTSB, the same body that is responsible for air accident investigations. Turning to assisted living robots, standard ISO 13482 sets out safety requirements for personal care robots. The standard covers mobile servant robots, physical assistant robots, and person carrier robots, but not robot toys or medical robots. There is, to date, no explicit regulation or regulatory body governing the use of assisted living or personal care robots, nor are there any systems or processes for investigating robot accidents, although serious workplace accidents are investigated by the UK Health and Safety Executive. The question then is, does the regulator have the protocols and expertise to be able to investigate accidents involving personal care robots? Next, let us consider AIs such as large language models or chatbots. In a recent paper on the relationship between benchmarking, standards and certification in robotics and AI, we surveyed the current state of certification and related standards in artificial intelligence. It is clear that in AI, regulation remains a work in progress. Almost certainly the first AI regulation to become law will be the European Union's AI Act, which aims to ensure that AI systems used in the EU are safe, transparent, traceable, non-discriminatory and environmentally friendly. However, the good news is that AI standards development has been underway at pace. In addition to the IEEE 7000 series standards I mentioned earlier, the ISO IEC Joint Technical Committee 1/SC42 on AI has published 20 AI standards since 2018, and a further 30 are in development. As I have explained in this talk, there is no shortage of sound ethical principles in robotics and AI, yet there is little evidence that those principles have yet translated into practice, i.e. effective and transparent ethical governance. Ethical practice starts, of course, with the individual, and emerging professional codes of ethical conduct, from the IEEE and ACM for instance, are very encouraging. But individuals need to be supported and empowered by strong institutional frameworks and principled leadership. What would we expect of robotics and AI companies or organisations who claim to practice ethical governance? In our 2018 paper, we proposed 5 pillars of good, that is, effective ethical governance. These are: publish an ethical code of conduct, provide ethics and responsible innovation training for everyone, practice responsible innovation, that is ethically aligned design, and be transparent around ethical governance by, for instance, publishing transparency reports, all underpinned by really value and believe in ethical governance. Note that these pillars would be equally applicable to all technology, not just robotics and AI. This concludes my presentation. I must express thanks to my colleagues on the IEEE P7001 Working Group, the Robotips project team, especially Professor Marina Girotka, and UK EPSRC for their support and funding. If you have questions on any aspect of the talk, please feel free to email me. Thank you.